Recording is started. All right, so the screen is being a little bit funny, so I won't be able to jump back and forth between coding and writing, so that's fine. We're going to go ahead and learn about one other data structure today. We're then going to leave some time to look at the project, so you just have a general idea of what you're going to do over the weekend. I would encourage you to start on this project. Just so you have an idea of the scope of it, I want to spend some time talking about it. It honestly isn't a very code-heavy project. I'd say if you're writing more than maybe like 20, 30 lines of code, you probably need to think about how you're approaching it, because it's a very, but it's just to make sure you know your way around different classes and things like that. So I'll talk about that a little bit at the end. But then we'll probably do kind of a lesson similar to lengthen this one on Monday, where I want to talk about one other data structure on Monday. Then Wednesday, and once we're done with data structures, Wednesday and Friday will kind of be just work on projects and kind of get ready for project 7, which is the choose your own adventure project. So I'll kind of give you some examples of things you might want to do. But let's go ahead and, like I said, we're going to start off today with just a few notes about another data structure. So just to kind of get our minds back on where we were, we're good with linked lists. We learned that last time. What I would encourage you to do is kind of code those up yourself, maybe do some Googling and just look at some different examples, play with some linked lists. And again, I will give you some more details about the final, which will have data structures on it as it gets closer. The big thing that was, that we're kind of observing, and we saw that highlighted right here, is that there's a trade-off. That if you want something faster, you may have to have something bigger. But if you want something smaller, like for example right here, to access an array right here, it was constant time, but it was expensive to append to it because we have to move things around in memory. So what we're going to look at now is essentially a compromise between arrays and linked lists. And the idea that we're going to do is we're basically going to take an array, but we're going to allow it to be like two-dimensional. So let's go ahead and let me go down to the next page, and we'll talk about this next type of data structure that I want to introduce today. So it is called a binary search tree. So a binary search tree, or a BST for short. This is the best. No, just the BST. It's missing me. There are a lot of trees. There's our pros and cons to each one. The binary search tree is very good for searching. There are certain things that are an issue with it, such as balance and kind of random access that we'll talk about. But there are a bunch of different trees, data structures. There's black-red trees. There's AVL trees. But this is a nice, there's again even non-binary search trees, and I banged my head for about 3 days trying to use a binary search tree to solve my last homework problem until the TA simply said, trees don't need to be binary. I'm like, oh. So that took me about 15 minutes to implement and was nice. So binary, of course, means 2. So let's go ahead and draw a binary search tree, then we'll kind of describe it. So just like linked list, we're going to have nodes. So we're going to have a node right up here at the top. And let's just go ahead and throw a number in it. Let's go ahead and just throw the number 4 in here to illustrate it. So that right there is kind of the root of the binary search tree. So let's go ahead, and this right here is called the root. Then what you'll do is you'll have a pointer going to the left, just like linked lists kind of had a single pointer. A binary will have 2 pointers, one going to the left and one going to the right. So what we want to do is when we go to the left, we're going to put values that are smaller to the left. And we'll go ahead and, let's put 2 right here. I don't want to overcomplicate this too early. So let's just go and put 2 there so we can have room for another level of the tree. So let's also then go to the right, and let's go ahead and just put the number 5. And So you can kind of start to see what is one of the characteristics of a binary search tree, and that is any value to the left, any node to the left has a value that is smaller than the root's value, and any value to the right has a value that is larger than the root's value. So let's go ahead and look at right here. What is, let's say we wanted to put 1 in this tree. Where should we put it? Should we put it to there, or should we put it here? Or does it matter? We actually, it does matter. We want, and again, I haven't written this in Word yet, but we want it to go here. What we want to do is we're going to want to search through this. So what we're going to want to do is if we see 2 and we're searching for 1, we want to go descend down the left tree to find smaller values. So we'll put a 1 here. Let's go ahead and put a 3 here. And let's go ahead and make 2 more leaves right here. And let's make this one, we got to be careful here about this. This one we really don't have any candidates for right now, because if you think about it, we already have 4 right up here. We have 5 right here. So let's just leave this one. Let's leave this one at empty, but we'll just call this none. Basically, this will just be an empty node. And what is, I don't know, what's someone's favorite number greater than 5? 7. Really, poor 6, just got skipped right over right there. So this right here is an example of a binary search tree. Let's go ahead and write in words what we're looking at here. So it's a tree where every node has at most 2 children, hence the word binary. So that's where the binary comes into play. And there's 3 properties about this. And so such that, I'll just do ST for short. The 3 properties are, 1, the node, its left value, so I'm using this dot notation to maybe shorten it. So if you look at a node, it has a pointer going to the left. The value of that one on the left should be less than the node's actual value. It also is the scenario if you look at the node on the right, its value is greater than the node's value. And that node.value is the root at the first step. So more on that in a moment. And the third property is the binary search tree does have a limitation that this data structure does not want duplicates. It's primarily used for searching. So we just want to check for the existence of something so it has no duplicate nodes. A little bit more on the terminology. If you have a root, you actually then have leaves over here. And you have leaves all the way down. You may also talk about the actual height of the tree. So if we're looking at how tall it is, in this case, you have specifically that the height is equal to 3. So the height is 3 here. And there's one other thing that's interesting about binary search trees that will kind of call back to something we did later or earlier in the semester. If I were just looking at this little part of a binary search tree, what I've highlighted or circled there in red, what is that little thing that I've circled in red? Say again? It's a triangle. Okay, that's the shape I was going for. But it's another binary search tree. If you look at this, if you were to look at any single non-kind of terminal node, it is another binary search tree. So if I look at this, so there's this idea of this, sometimes this will be just calls a subtree. Can anyone else think of an idea from earlier in the semester where we started with one thing and then we had the same thing but just a little bit smaller? Recursion, exactly. So there's some natural recursion built right into this type of data structure. So let's go ahead and before we code it up, let's maybe just think about what is the time complexity to do some basic operations on here. So let's just maybe think about searching first. Let's suppose we were to search something. This is called a search tree, so it would be nice if we can search it quickly. So if we're looking at this, so let's say you wanted to search for the number 4. How many steps would it take you to find the number 4 if you started right at the root? 1. You find it right away. Let's say you wanted to search for the number 5. How many steps would it take? 2. If you wanted to search for 7, it would take you 3. What if you wanted to search for the number 9? How many steps would it take you? 4. What about 100? 4, right? This is the worst case scenario. That is to say the numbers are not in the tree. So you still search for it and you just say, oh, it doesn't exist. So if we think about this, we have how many nodes do we have here? 2, 4, 6, and again, we could count none. So basically here we have 8 nodes. And at worst, a search is taking, let's count where they are. 1, we would search, let's not do that. So we'd search 1, we would search 2, we would search 3, and then again, we'd realize that, well, let's see. If we were searching for 8, we would search here, we would check here, we would check here, and again, one more check, we would realize we'd be at none. So therefore, we're basically out of places to check. So it is taking 4 steps. What if we went ahead and added a few more? Again, if there was more right here, more right here. If you think about this, we could have added 8 more nodes and only increased the height by 1. So what type of what kind of pattern are we developing in our worst case scenario? If we added 8 more nodes, it would just add 1 more to the steps. It's logarithmic. We basically could increase everything by a factor of 2, but it only takes 1 more step. So what we have right here is a logarithmic search. Logs are amazing. I don't think college algebra appreciated that this morning, that when I said we could take the log of 100 and then we can go to like a log of 10 million and the output only increased by like 7. Like they're like, I'm like, okay, fine. Not math majors in here, I get it. But it's such a cool function. Plus, the logarithmic rules are so much fun. So this is a really nice thing to maintain because remember, if we kind of think about the issue that we had earlier, we had logarithmic search and arrays, but the issue was when you tried to append something, you might have had to move the whole array just to get it to fit. So we're now taking this idea of linked list where you didn't necessarily have to move things around to make things fit in memory because we're still using pointers, but we've got our logarithmic search back. But okay, that means, let's think about this then. So we got our logarithmic search back, thank goodness. But what if we wanted to insert or if we wanted to append something to this? So let's think about how many steps would it take to add something to this tree? Okay, so think about the worst case scenario. What would be the most, so again, it does depend on what it is, but what would be the thing that takes the longest to add? Something that would go all the way at the bottom of the tree, right? So what if we wanted to add 100? How many steps would it take for us to add it? We would have to traverse it, again, because remember, these are technically all over memory. That's what these are not contiguous in memory. The arrows said they're floating around somewhere on the computer, and each of these is basically storing a pointer telling us where we need to go to find the next node, so just like linked list. So how many nodes would you have to traverse, though, to add 9? Yeah, that's the worst case scenario. If we wanted to append 9. 4. So it's really the same thought process of searching if you think about it. We just got to, if we need to go ahead and add 9, we don't need to worry about this because we need to go over here. We don't need to worry about this. We're basically cutting the problem in half each time. So to add 9, we're basically just searching down these pointers. Yeah.
What if you were to add like 5?
So if we were going to add 5, we'll look at an algorithm on to insert it, but it would be a duplicate one right here. There are also things that we want to be careful about when it comes to balancing things. So let's maybe just do a little example over here. Let's say we have we have 10. Let's say we have 4, and now we want to add 5. Well, let's also actually say we have 13, or let's say we have 13 over here. Well, to add 5, we want it to. So let's see, we would want 5 to go over here because we don't want it to exceed the value. That's the part of so 5 does not go over here. And if you look at this one right here, you would go here, so now 5 would go right there.
Oh, so everything on the right side of 10 is going to have to be bigger than
Yes, and everything to the left must be smaller.
And does that extend to 13 too? So if you were to go to 13, it would have the left side would have
Because every node is its own subtree. So let's keep this okay, what number do you guys want to insert now? What is it? 15. So 15, we go here. Is 15 greater than or less than 13? So we're going to go down here and start 15. What if someone else give me something they want to insert? 3, okay. So we go here. Is 3 less than or greater than 4? Less than, so we go here and we do 3. Now what do y'all want to insert? 11, okay. So 11, so we go here, so it's greater, so we go this way. Then we look at 13, it's less than, so we go ahead and search and insert it there. Then do we want to keep this going? Y'all having fun yet? Let's try something in between. So let's try something in between 13. So let's say what about 14? Well, 14 would go here, and then 14 would go here, and then it would go over here. So if you notice, every time you're trying to insert something, you're essentially chopping off half the tree. And anytime you try and cut something in half, what type of time complexity are we looking at? So logarithmic again. So again, we have our logarithmic insert. So this is kind of a downside compared to linked list. So because remember, linked lists, we could go ahead and just append it and it was just some constant time. But that's because we didn't necessarily try to maintain any ordering in a linked list. A binary search tree, we're trying to maintain an ordering in a property. That is to say, the left node, these right here, the left node's value is always going to be less than the value of the node it's coming from, and then the right node's is going to be greater. Does that make sense? Does that help? Okay, and then honestly, the last thing we want to go ahead and think about is access. To access a node, this is also done in logarithmic time, just kind of that same thought process that we went through for inserting. You just essentially are going to do a quick comparison for each node, whether you're going to be looking to the left or the right. So let's go ahead and take this structure and code it up, just so we can kind of get a kind of a actual computing feel to it. But that's a binary search tree. The last data structure, which we're going to talk about on Monday, is a really nice structure because you can go ahead and actually search it in constant time. It would be nice if we had a data structure that doesn't matter how big the structure is, it's just a constant time. Yes, Seth?
You said for your homework that your professor said it doesn't have to be binary, so would that be like 3, or how would you do it?
So the problem that I was looking at, let me just kind of, mine was not a searching problem. The problem I was looking at was basically a distribution problem the problem, just if you're curious, I have one node that has all of the data. And I have 3 nodes right here. No, let me write it like this. Let's look at this. This is basically, this was my root, and I have A, B, C, and I have D. That is in the root. Then I basically have a couple other processors. So this was like processor 1, this is processor 2, this is processor 3. These are different computers, and I need to get that data to the other one. And basically, the algorithm I was thinking of is, okay, each of these needs the data as fast, so I'm going to just take this data, give it here, and then this data and put it here. So like then I would have A, B here, then I would have C, D here, and then then I would have this one send it here, and then I'd have this one send it here. So I needed to distribute that data to all of the different processes, something like that. And for some reason, I kept doing this binary, but you had this asynchronous communication that basically said, just start the send there, start the send there, start the send there, and then let the actual module or the library basically handle it. So I kept trying to force a binary structure where I should have just said, send this here, send this here, send this here, and you can see that's more ternary than it is binary. So I just got stuck in binary trees for some reason, but you can have trees, and this one was more of a ternary tree that I was looking at.
So when you have like that, when we have the number ones, you're doing like greater than, less than. How would you do that? You would be looking at a different type of problem. Yeah. Searching, you want to be able to go left or right. Now, I might be able to redact that next week because my next project is I essentially have to do a sorting algorithm with parallel processing, and I don't know how that works yet. So yeah, but my problem was more distribution of data than it was searching of a large data structure. So anyway, let's code up a binary search tree and kind of see how these nodes could be linked together. Any questions on this structure that we're looking at? Okay. So let's switch to a REPL. All right, let's just get an empty REPL. Where's my cursor? That is so confusing. I have no cursor right now. Shows up there. There it goes. Okay. I'm going to call this one BST. So it's just going to be a standard Python REPL. All right, so here we go. It's going to have a feel similar to the linked list. That is to say, we're going to have a node. So let's just go ahead and define a class called node. It's not going to inherit from anything. It's just going to be a base class. Let's go ahead and define a constructor or initializer. It's going to take self, and it's going to take some sort of value or some sort of key. So every node, there were 3 things going on with it. It had its value. So self.value is the value that you construct it with. But then, of course, it also had two things: a left pointer and a right pointer. So we're going to say self.left is just going to point to nothing at first. And then we'll have self.right will also point to nothing. So while we do have, just throwing this out here, so while we do have our logarithmic searching algorithm back, that's nice. What was the cost? The nodes are bigger. Remember, a node in a linked list just had the value and then one pointer to where to go next. This one you have to have store basically 2 pointers, which are to 2 other nodes. So by the way, let's also go ahead and define a string class just to make this a little bit more readable. So let's just go ahead and let's just have it return a string of the value. So self.value. So nothing too fancy right here. Let's go ahead and create a node. Let's call this our root. It's going to be a node, and let's do that one that we initially created. So the one we initially created had a root of 4. Sure. So, and let's go ahead and print root. So print root. All right. So there's our node. If you, again, just to verify, if you could also go ahead and print root, and then you could also print root.left and root.right, just if you want to see everything that's happening there. It has nothing pointing to the left, nothing pointing to the right, and when you just call print, it's going to give you just whatever the value of it is. Any questions on the node we're working with? All right, so let's actually go ahead and start constructing that tree that we just made a little bit. So what we're going to want to go ahead and do, let's see, root.left, we want that to be a node with a value of 2 in it. And root.right, that was going to be a node with a value of what in it? What do we say? 3, right? Yeah, 3. So now if we go ahead and print this, let's go ahead and run that. And just to have something for reference so I don't have to keep peeking over and so we're all on the same page, I need an eraser. So go ahead and think about how would you then build the rest of the tree. So we're trying to build that first tree that we did in black. So I got us started here. We have root with node 4. Then we have the left is a node of 2. And how would we finish building the tree? That, what did we have? We had 4, then we went over here to 2, then we went over to 1, then we had 3, then we had 5, then we had none, and then we had 7 was Lois's favorite number. So this was the one we put in the notes, right? Yeah, so how would we finish building this tree? So of course I have this one. Oh, this would actually should be 5 then, yeah. So let's make that 5. So that's that first one. How would I get 1 and 3 on here? Any ideas how I could notate that easily? I mean, there's a couple ways you could approach this. Anna? Well, we can go ahead and do recursion, which we would have to then define a function that would do that, and we'll do that a little bit later. So that's kind of what we're going to work to. But if we're just manually building the tree, Anna? Yeah, so what would I have to type to finish building this tree?
Well, do you want them like 4, 2, 1?
Just this structure right here. We're manually building the structure ourselves. So we want 1. So right now we have this is in there, this is in here, and this is in here.
Oh.
So how would I get 1 in there? Close. So we're definitely going to need to go to, so we're going to need to go root.left. And then what do we, so that puts us here. We need to get down here, so we need to use a pointer. Caroline, what do you think? So dot value would give us this right here. We need the pointer, so we would not do dot value, we would do dot left. So root.left.left is going to be a node with value 1. And let's just go ahead and just, by the way, look at, let's just kind of print this just to see what we're looking at. Let's go ahead and print root.left.left, and you can see, let's go ahead and run that. That prints the 1, because remember if you just call the way we have our string method, when you just call print, it's going to do the value. So that's how we put the 1 in there. Okay. So how would you go ahead and get the 3 in there? Anyone want to take a shot at that? Yeah, it would be root.left.right is a node with a value of 3. And then let's also go ahead and get 7 in there. So root.right.right is a node with value 7. So if we think about this, though, we have this whole tree in there. We need to go ahead and figure out, what if we wanted to print this tree? So this is where the recursion is going to start to come into play right here. So any questions so far? Okay, so how are we going to do this? So let's go ahead and just, again, we could wrap all of this in some sort of BST class or binary search tree class, but let's just go ahead and just define a function called print BST for a binary search tree. And how do we want to print this? Like, how would we want to print this tree? What would you want to be printed first, then second, then third? What do you think? You want to maintain the order, right? Yeah, so it would be nice to print here, then here, then here. But then you want to print there, then there, then there, then there. One thing about trees that, again, if we were to maybe spend more time, there are on a lot of computer science degrees will have, like, honestly 2 courses just purely on algorithms and data structures. So what we're doing, so like there's a lot of depth that you can go ahead and do what we've done in the last 3 weeks. There's 2 courses you could take in typical undergrad, but what we're going to do is known as an in-order traversal. We're going to go down here. We're going to basically print all of the nodes attached with 1, which is just none. Then we're then do 3. Then we're do 2. Then we're do 3. So we're do all of the left side. Then we're going to go up here, and then we're going to do all of the right side. There's you may also prefer like a breadth first, like you could print 4, then 2, then 5, then 1, 3, then none, then 7. So again, it all depends on the problem. But what we want to do is basically an in-order traversal. So we'll go ahead and print the BST in order. I just wanted to mention that there's many different ways to interpret the printing of a tree. So what do you need to pass into this? Well, if we're not in a class right here, this is a function, so this is not in a class. So we're going to take a function, and we want to print the tree. So how do you access the tree? Through the root. So what we want to go ahead and do to print the BST, we want to go ahead and give it the root node. This function will do the transversal through the tree. So we'll go ahead and it's going to be some general R, and then again, we're going to do stuff here, but we're going to go ahead and print BST in order, passing in that root that we created. So we want to print this right here, and let's figure out this how to implement this function. Okay, so what we're going to do is we're going to first check that R is not equal to none. So, why do we want to do that? Well, if it's none, there's nothing more to print. So that, of course, checks to see if you even have a root or a node to begin with. But again, if you think about this none right here, there's nothing to print here. So we want to make sure that what we're about to print is not equal to none. So what then we're going to do, we want to do this. Here's my triangle again. You guys liked the triangle, so here's my triangle again. We just want to print this tree right here. So what we're going to go ahead and do is we are going to call that function itself, but let this be the root of the tree we want to print. It's recursive. It's a very natural recursive structure. So what I'm going to go ahead and do is print the BST in order, but what is this right here? It's not root. How do I access this node? I have to traverse by using the pointer, so I would do r.left. So r.left is the node that's 2. Okay. So I'm going to want to print that. So again, now if you think about this, it's going to go in here, and then it's going to look at just 1. And then is going to go ahead and see none. So eventually we're going to get down to none. And what we want it to do is actually print the value of this one right here. So to do that, what do we want to do? We just want to go ahead and print r dot value. So the way this is going, we recurse down, we look at this tree and this triangle. We recurse down, we look at this triangle. Then notice here, we recurse down, try to look at the subtree of 1, see none, so that just does nothing. As I come back, print the value, so now 1 will have printed. And then, of course, it'll try to go down to the right. We still need to talk about going down to the right. So what will that be? So again, this will be none, but how would we go ahead and print the tree on the right? Well, you would just do a recursive call, but what would you pass into this recursive call? r.right. So r.right. So again, let's trace the logic right here. You would call it with this subtree, you would call it with this subtree, and then when you try to call the left, you would realize that r.left here is none. Then you would go ahead and print this, and then you would call it on the right, but then you would realize that the right is none. Then you exit back off that stack frame, you print this, you do the same thing with 3, and then you go ahead and go back up here, print 4, and then you print the right-hand side. So let's go ahead and see if that works. You can see, no, and just by the way, to clean this up a little bit, just so it is a little bit easier to read, I'm going to go ahead and end this with just, I'm going to change the end from new line to that, so let's now run that. So look at that. We have our order, 1, 2, 3, 4, 5, 7. So a binary search tree has a very natural recursive structure that allows you to do a lot of searching by just chopping off part of the tree. It's like all you have to do is one conditional and the tree is gone. So that's something a little bit interesting to think about. Anyone have any questions so far? So what if we want, maybe here, let me give you a little bit of an exercise now that we're talking about searching. What if we want to search BST? I'm going to go ahead and give it some sort of R for the root, and let's go ahead and search for some N. So how would you go ahead and search for some value? So let me give you a moment to think about how would you go ahead and search a binary search tree for some value. Let me give you maybe 2-3 minutes here. Hint is going to be recursive. So think about what way do you want to go depending on what value of n. So our goal here is to write a function that will search a binary search tree for some with root r at some value n. 30 more seconds, see if you made any progress. And again, I wasn't necessarily expecting you to get it, but just something to think about. Anyone think they got it? No?
I think I know like what you want to do, but I don't know how to write it.
Try to describe it. Seth, how would you do this?
If R is less than root, move left.
Okay.
Down, and then you would write it recursion.
Okay. So what's the base case?
If R is less than root.
So that's what's causing us to move. So what's the base case? There's two things that could happen. The value is you're looking at the value, or so that would be the case you found it. What would be the other case? Seth, what do you think?
It's not equal.
Is what?
It's not equal to the value, so you have to move right or left.
Okay. And then when do you want to stop? When can't you move any more left or right?
When it is equal.
When it's null or none. So that basically is our four cases right there. You either found the value, you did not find the value, or the value, you did not find the value and you're none, or you did not find the value and you can go move left or right. So there's four cases. Let's go ahead and code up those four cases. So the scenario that we're at is going to be recursive, so it is going to be that R that keeps passing down. So if R is equal, let's just say if R is none, well, this is kind of the scenario. Let's do this one first, because what if they pass in basically a tree that's not constructed yet? So if R is none, then what you'll want to go ahead and do is return false. This is the case where, of course, there's no tree. You weren't able to find it. So Elif, the scenario that you're looking at, is that the n that you're searching for is going to be less than r dot value. So let's think about that. If the value of n is less than the value of the current node that you're looking at, what way do you want to go? Do you want to go to the left or to the right? Say again, Anna? You want to go left, because it's not the current value. So we want to go left. So let's go ahead and do here's what we're going to do. We're going to return the results of searching our binary search tree, but our root this time is not going to be root. It's going to be root.left, and we're going to pass in the same n. We don't want to change what we're looking for. The other scenario is that n is greater than r.value. So in that case, we're going to go ahead and search the BST to the, I put the wrong, R dot right. I saw R and I'm like, right, no, that's just R, the root. And we'll still pass in n. And then if it's not none, it's not less than, it's not greater than, well, what is the last case? Say again, Karen? It's equal to. And if it is equal to, what do we want to return? Some options. What do you want? What did you say, Caroline? So you could return the value you're searching for, and that might be one way to indicate success. You may want to return a string called success. I'm going to just go ahead and return true since we did false. So again, that question was really kind of an open-ended one. So then it would be return true. So let's go ahead and try searching for this. So let's go ahead and search BST. Let's go ahead and look for, the root was 7. Let's go ahead and look for 7. Let's go ahead and run that. R is not defined because I called it root when we're outside the function. So you can see that I need to print that. I'm getting there. So I need to print the results of searching. So you can see that indeed was true. Let's say we were searching for -2. You can see that would be false. If you want to search for, I don't know, let's search for that number. You can see it's false. Because imagine if you were searching for that number in a large array, it would have to do a lot of searching. But that's a binary search tree. Does anyone have any questions on that data structure? Okay. Let me go ahead and take a few minutes here just at the end of class to talk to you a little bit about this next project. Is that fine? I'll give you some hints for the weekend. All right. So the next project is the reading is all going to be contained within the actual REPL. So I just think it's easier that way, just so you can keep track of it. So let me go ahead and go to, let's see, Teams. So we're all in the same team. Let's open this up. Okay. This one is called geometry. Y'all know some geometry, been through, circles, shapes, etc., etc. So here's what this project is going to do. When you go ahead and load it, you're going to ramble until it's ready. So the main.py, what I want to make sure you do is read everything in the doctrines at the top of the file. So for example, this is the entrance to the program. Read this line. You do not need to do anything in main.py. You do not need to modify it. It is basically the driver code for this project to help you think about it. But if you run it, let's see what's going to happen. So if I run it, this is basically a little app that we've made that's going to help someone study geometry. So I just called it, I don't even can't even read that in the right now. What did I call it? GeoLearn, that's what it was. Thank you. It's hard with that light. So this is a little app called GeoLearn. What you're going to do, you can add shapes. So if I hit 1, it's going to give me some prompts that with some basic shapes in here. I've given you some samples in here. If you look at triangle, so I'm going to do T, and you can see it's going to be comma separated. So what's, by the way, 1, 2, 3, is that a valid triangle? There was an exercise way back earlier in the semester. There's basically, you have some conditions you need to check. You don't need to worry about that part on this project. The code that handles that is already written for you. If you're curious where it is, it's basically this right here. There's already some code that checks if the valid is triangle, so you're not needing to worry about that. I would encourage you to read through this code, but you don't need to really do anything with it. So if you look at that, I've added a shape. Now if I hit 2, show all shapes, it basically will make a table of all the shapes that you put into this. So you can see right here, the SGR of the triangle is right here. It did some computations, perimeter 6. It's done some formula. The area is 0. That's a little bug. Don't worry about triangle. I've already implemented it, but there's something off there. I'll look at it later. Anyway, what I want to show you what you need to do. Let's go ahead and run this, but let's say we want to add, what non-triangular shape do you all want to try to add? Circle. What's the radius? 2. Circle of radius 2. It says to do added successfully. Well, that's probably an indicator of something you need to do. And again, notice here, if I click show all shapes, it has 0, circle, string to do, perimeter 0, formula 0, area 0, formula 0. So obviously that is not right. So what you'll want to do is you'll want to go ahead and look at the the triangle class to get a general idea of what these classes should look like. So if you look at the triangle class, I've given you some information. It is completed for you. Model your implementations of the other classes after this one. I've talked a little bit about style. I am expecting some styling to be proper on this one. So part of this assignment will be reading the PEP 8 style guide. Basically, PEP 8 is put out by the, PEP stands for Python Enhancement Proposal. So basically, these are proposed to python.org, and they accept them and they use it to iterate. So you'll want to read through it, and that's essentially a basic style guide for how you should write maintainable, documentation for Python code. But look at here. You have init, you have get area, you have get perimeter, you have a string method. Everything is nicely documented. It has some returns. So of course, now if you look at circle, it has nothing. No doc strings. It has placeholders. So what your goal is basically going to be is to implement the other 4 classes. And you can always go ahead and read the instructions down here. where I kind of summarize that. Read the PEP 8 style guide, experiment, understand the starter code a little bit, implement the 4 remaining classes, circle, pentagon, rectangle, and square. Remember that every square is a rectangle, so you have inheritance to consider. I've already implemented equilateral triangles, so you have an example of what inheritance could look like. And there's some extra reading. Class method is not something we've really talked about, but it won't hinder you from preventing this project since you're just doing the logic. You can just, that's already set up for you. So like I said, honestly, this project isn't going to be a lot of code. By the time you put in doc strings and things, it may be a couple, maybe 100 or so lines, but the actual like Python code, very few lines. So a lot of this is making sure you understand your way around classes. Monday, we're going to talk about one other data structure, and that pretty much wraps up the content. So think about what you'd want your choose your own adventure to be also. What would you like to learn how to do that we haven't learned in this class? That will be your project 7. I'll demo some ones next week. Any questions on the day? All right. If you have questions, as always, feel free to stick around. Otherwise, I'll see y'all next week.